Hello ladies and gentlemen, welcome to our second part video on linear models. Last time we finished discussing the Kang people and modeling of their population. As I said before, the Kang are part of the San people. There's a nomadic tribe that lives on the western edge of Kalahari Desert, and this is a well-known one of the well-known isolated populaces of people, which can be very easily investigated from the anthropological point of view, and is one of the its population from the 60s, measured and investigated by Nancy Howell in the 60s, and this dataset we will be using today. This dataset comes from the Rethinking package, and that is part of the Statistical Rethinking book by James McElrath and Richard McElrath, and this book is and we'll be using the dataset from this book. So let's create a linear model depicting of the heights of Kang people. Starting with standard, we go to the Jupyter notebook. We have the input necessary packages, certain visualizations. We are getting certain ribbon plot that we've used last time, some variables from DA tools module that will be given in the you in the GitHub repository. And what are we doing here? We will be loading dataset directly from the McElrath's package, and here it's you can directly download it from his GitHub repository and use it with pandas to load the data. And probably to start to make our modeling problem easier to see certain aspects, we'll just focus on the adult population of Kang people, because we can assume that at least there will be not as much variance in the heights. That will be certainly age dependent. So we can see our dataset is relatively simple. It consists of the height, our variable of interest, weight of such person, their age, and binary encoded gender. And we will start with the most simple model, a normal model. Normal model generally makes sense, as we've talked before. The normal models are good for modeling of small increments. Height is a small increment because generally we grow in small bursts over time. Our growth is not continuous. There's short spikes of small adding of your height, increase of your height through your entire adolescence and childhood. So, without further ado, we can start discussing what will be our model. If we have a normal model, so our model will be a normal distribution with mi and sigma. Mi and sigma will need to be estimated. We need to assign priors for that. For our prior predictive checks, we'll consider two priors. First, the prior for mu. So the prior for mu would be how we expect the height of the population as average. Without looking at the data, if we consider, for example, average height in Europe, it is around 178 centimeters, so a bit under 180. In order to have a big spread, we can assume that we'll get the large standard deviation in that prior. So we'll have a well spread distribution, and we can assign, for example, standard deviation of 20 centimeters. Because of that, our prior will give us information that mean should be for 95% between 138 and 218 centimeters, which gives us a very large spread for adult people, that will not interfere without any other data. The data that would provide much higher heights would be would have to maybe problematic, but we don't expect that. In order to get a good spread for a good spread for the standard deviation, we are assigning the exponential distribution. Exponential distribution, as we told before, is a good prior for standard deviations because it gives you the not so thin tails as in Gaussian distribution, or like half normal distribution in this case. And in this case, we've put the mean around 15, so we'll get this is the representation of this parameter. It's one by the coefficient of exponential distribution is inverse proportional to the mean, so mean of the distribution. So using that, we get the mean around 15. So we have this model. We first create our very simple prior predictive check model without any data, without any parameters. We just created with only the generated quantities block, because this block will allow us to simulate our data. So like compilation of this model is straightforward. We don't use any fireworks in the simulation, nothing special. We have 3 parameters. The parameters we are interested in, so me, and the 2 parameters, me and sigma. So the points we are estimating, and we are simulating heights from this model in order to see how our predictions will fit what we wanted to have. So starting with our priors, we can see that priors were generated without any hiccups. Means simulated with this model are consistent with priors, along with sigmas, which is also consistent with prior, so there are no numerical issues with simulation. The simulated heights are generally feasible. Of course, we assume this model allows us to get some really tall people, but we have not broke the world record of height, and we still have not got below 0, so both those things are relatively okay. So this model, prior analysis says results are reasonable. We haven't used data to look at it, we just used our common knowledge. So average height of people in Europe, because this is what we have. We can, with large spreads, so we can cover very well a lot of heights. We give a good well spread prior for sigma, but like not absurdly spread. It just gives us the information that we can get up to 50 centimeters, at most 50 centimeters of standard deviation. So the spread can be large, but not absurdly large. And simulated data make kind of sense that they at least do not lead us to absolutely infeasible results. So let's create a model. Model will be a bit more complicated because we need to introduce some data. So the number of samples and those samples. We need to add the our parameters for our models, so which we want to estimate. We assign them priors, and we create the likelihood that makes how our data fits to our samples. And for additional reference, we are adding the generated quantities, which we'll see how the simulated height will work. Of course, doing a model can be compilated, and the data for it will be generated here in line with a dict function. So it will be the len. The n will just get us the length of the data frame, and the values we'll also take from data frame. And look that we are not putting a column from data frame here, but we are putting here and NumPy array that are the values from that column, so that will be more efficient for this use. And we our simulation, when we use the summary function, we can see that the mean height from our estimation is around 155 centimeters with a very small and this mean has very small standard deviation, and its confidence interval In this case, it's an 94% confidence interval, and it's between 133 centimeters 8 millimeters up to 155 centimeters and almost 4 millimeters. And however, the standard deviation is relatively large. We get a spread of up to almost 8 centimeters here. The spread, this confidence interval for this standard deviation is between 725 to 837. Well, let's look at the visualization. So, sampling from this posterior, we can see that this distribution is relatively centered, normal-like in its shape. We get the samples are here we've used kernel density estimator to create this two-valued distribution in order to see that its mean is located around the maximum of the distribution. So those samples are consistent with those. This plot was generated using these samples. And if we look at our model, we can compare the predicted height to the observed height, and as you can see, of course the predicted height is kind of Gaussian. However, the observed one there is something that our model is not capturing really. There is some cut. We are not observing this part of tail. We have these spikes here, which might be related to something else. So generally, this simple model gave us some kind of information, but it just kind of a summary of our data. It just gives us this is a marginal distribution obtained of what our data could look like. We can, however, focus on a more advanced model, so we can add predictors. And generally, this is the philosophy that you should follow all the time. Start with a simple model and complicate it. Don't go with the advanced model and try to simplify it. That is much more difficult, because when you are complicating your model, you're adding additional predictors, additional functions, additional modifications, you see what the part you've added gave into your model, so you can trace back easily. When you have a complicated model, removing parts of it makes it much more difficult in order to see why certain removal helps or not. So let's add our predictor. We have multiple predictors in our model. However, we have 3 potential predictors in our dataset, but we'll focus on weight. Why? Because generally we are not here trying to create a causal model, what causes the height of certain people, because our data wouldn't allow it, really because it doesn't contain enough information, but we can create a predictive model. And it is rather obvious that the taller people will weight more. So adding such predictor makes certain sense. But generally, what we want to do is we want to have our model on one side extendable from to more complicated situations, but we want to make it rather interpretable. And really, that's why a very desired property when creating this model is centering of variables. What does it mean? It means that, for example, when we are considering our predictor, we want to focus not about the value of we don't want to consider weight scaling in natural variables, but we want to see how weight changes as a deviation from its mean. Why? Because our predictor then would be on a smaller scale, spreading from negative to positive values, but also when the we have now the interpretability of the intercept coefficient. Because remember, linear model consists of the intercept and linear functions of predictors. If we use the centering situation, we have an interpretation of what the intercept is. The intercept will be the value of how the model would behave if the predictor of interest would be at its mean value. In case of creating a model of height depending on the weight, the model of what the value of height will be when the weight is equal to 0 makes no sense. But that would be the predictor. If the variable wouldn't be centered, then alpha parameter, the intercept, would mean that it is the value of what height we expect when the height is equal to, when the person is 0 centimeter tall, which makes no sense, because 0 centimeter tall is an embryo, so we cannot expect to create a model that considers that. So the interpretability of the coefficient is lost. That's why the centering is useful. Not only that, it will also help in numerical computation and other stuff, but really, centering of variables is a good idea when creating linear models, just to start the, we will move further along this way with standardization, but let's start with centering. So we will have the centered values of our model. So we are just adding additional column to our data frame, the centered weight, which is computed very easily to get the representation of our model. So we can now start to do some predictive checks for our new model. First of all, let's assign some priors for our model. So we can assign the prior for alpha constant the same, because now it's still alpha represents the mean of population. So alpha is the situation when this part is lost. So this part is lost when centered weight is equal to 0. So the weight is equal to the mean. So for mean value of weight, we will have the mean value of height of a population of a person in population. So we leave the same prior for sigma. There's aspect of what coefficient for the from our beta what's prior for our beta coefficient, and we can start with a very standard model of normal with 0 mean and 10 standard deviation, which is very well spread coefficient. It will give us the it's almost flat in the area of interest. So we will have the we can consider well designed situations. Okay, so the model is again very simple. This time, instead of mean coefficient, we'll be computing we won't be computing one value of predicted height, but we will be predicting values of height for all given values of weight. So we will need to compute the mean of this our predictive normal distribution, which is of course a linear function of predictors and the intercept. So we will do it in a for loop and create simulate a sequence of our models. Then this model can be compiled. Of course, we can do the assign the data for our data for our simulation. We'll start with 50 samples, so it will be easier for simulate. It will be fast, and we add we need to add some weights for testing. So let there be a set of linearly spaced values between minimal and maximal centered weights. So we'll have good spread of values of our interest. Then we can get the we can simulate our model again without any complication. We are still working on the fake data, and we can extract those data and we see how looks our model, especially how the predictions look like. And here we've drawn, I think, 100 lines from our distribution. So we've sampled alpha and beta. We've created the lines of alpha plus beta times centered weight, and see how our predictions of our model would look like. And they don't look very well, because for our adult people whose height, whose weight is between 30 and 65 kilos, we have values that are relatively absurd. First of all, our model can get us to very large heights, well above the world record registered anywhere before, and also it can get us below 0, which is also not a very good situation. So really, our prior is bad. We need to assign some better prior for beta coefficient to get something, some more reasonable slopes. And the idea is to use one of the transformations to assign the values to enforce, first of all, positivity, because really we cannot expect from our model reasonably to get values to be negatively to height being negatively correlated with weight. Maybe there are some people that are taller but lighter, but this is not a general tendency. Taller people are heavier. So this relationship should rather be positive. But instead of using fixed bounds on our priors, we can change our model to include our prior for beta to be a log normal distribution. And log normal distribution is a distribution of positive numbers which for which logarithms of which are normally distributed. So we allow ourselves a bit of spread with values, so we can get both very small correlations approaching zero. Those will be corresponding to a negative values of logarithm of beta, and larger numbers. But in order to don't get too much spread, we get the standard deviation of 1, which generally gives us this 95% spread of from 0.01, so 100th as a minimal value, up to 100, 1 by 100 value as a minimum, and a 100 as a maximum of a gain of with 95%. So we will have this spread of our coefficients going off four orders of magnitude, but still they will be relatively small. At least they will all be positive. So we can go from almost zero association up to a very strong association between weight and height. And because such change, we can again do the prior predictive simulation, this time with log normal distribution as a prior for beta. And as you can see, that change is much more much more sensible. Of course, there are singular lines that have too large slopes, but most of them are still well fit in our pipe of between zero height and world record height in the weights of interest. Of course, we do not expect to get so tall person in our model, but at least those results are kind of sensible. Our model won't be predicting absurd values of giants or negative heights. So this model makes a bit more sense, and we can use it then for our additional predictive check we can use is the model is simulating the outputs, which we did as before. We haven't analyzed it because we've stopped at this point. But when we simulated the y values, the height values, then you can see using the ribbon plot, you can see that generally our data is not inconsistent with what we can observe. At least it is possible under the we have very well spread model. We have a bit higher mean, which moves everything taller, but we still inside the quantities of interest. So it's not that bad. So our model is relatively okay. So let's start with at least on the prior predictive checks level. So let's start with the posterior inference. So again, we take our model. This model is, we've added additional block of transformed parameters. This block will be useful for us, first of all, for visualization of how means behave with, for example, ribbon plots later. But also it makes our notation much sleeker, because really we'll be able to use vectorization here in our model, which is much more numerically efficient. You can read about it in the style manual. We provide our model with data consisting of number of samples, number of weights that were interesting, and the heights that correspond to them. Then we assign parameters alpha, beta, and sigma. We create a transport parameters vector that would correspond to the multiplication of weight and coefficient beta plus alpha. So we'll get this will be a vector of means for all of the samples that we are interested in, and our model consists of priors, as we stated before. For the intercept, normal 178 centimeters of mean, 20 centimeters of standard deviation. For beta, log normal with 0 mean and 1 standard deviation. For sigma, exponential with mean of 15. And heights will be corresponding to our model. So really, the model structure doesn't change much. It is consistent with what I've shown you before on the slides in the first part of this video. And we can again, using generated quantities block, sample from our model. But this time, mean is a function of weight and beta. So we have these values for each values of weight. We have appropriate mean that can be used for this prediction, and we are fitting it by sampling the distribution in this consistent way. So we compile this model and we can fit our model using our data we have provided. We will be using, at first we'll be using a small data set. We'll start with the 10 first samples, and then we'll be increasing the data set, so you will be able to see how the model changes, how our uncertainty about the model changes along with new data coming in. So we'll be using a shortened version of our data frame with only first 10 rows, and then we'll be adding more rows as our iteration go. Our model will consist of number of samples, these centered weights and the heights. We will sample with it, get some parameters, get a summary. So let's start with that. We get our model sample very fast because it has very little data. As you can see, the samples went very fast. However, there are some problems that come from something called divergences. This we won't be discussing too much at this moment, but really this comes from the situation that we have very little data. We have very little data, then our model will be relatively hard to fit, because if we don't have enough data to get our parameters, which we have free in our models, to get reasonable predictions of them. And because of that, the geometry that we have to analyze of our model is more complicated. So let's see how it looks like. The first 20 samples of our lines for our database give us very large spread, really. We don't have much certainty about what's going on. The data points, as you can see, are limited here, and if we consider the mean of our distribution, we'll look at the repeat, but this is also relatively uncertain of how long can we go. This just you can see also it here how it's going on, that we have the beta coefficient has a relatively large standard deviation, the same as alpha, with over 1 centimeter here, and the large sigma. And when we look at our predictions, then our predictions are very wide. Of course, they cover all of the data that we have observed, so that's usually good, but we have a bit of uncertainty of what's going on. If we increase number of data points, then the fit is much easier. There are no problem with divergences. As you can see, also it's still very fast because it doesn't require much, and there are no problems with fitting the model. We got better coefficients for alpha and beta. With alpha, we have much more certainty than before, and if we draw our lines here, they are for 50 data points. They are a bit more focused inside, and our uncertainty for the mean is much smaller because having more data, the more lines give us here. Remember, here is only first 20 lines, first 20 results for samples. We have 4,000 samples, so These are first them, so they are not they are much more spread than the mean here. Here we have a 90% quantile of what's going on here. So this will be certainly thinner than before. And if we go to the predictions from the 50 data points, then our spread is also smaller because we have more data. Most of them still fit. There are some others outside of this 90% area. If we again increase our data set, we need a bit more time in order to do some sampling. Our model still allows us give us similar results, and as you can see, the lines are again much more focused here, and the mean is even more focused. We have the mean we have relatively well estimated onto the data, and with our spread, we still are covering most of the data. There are some of them are more spread than others. And if we just move to the entire data set, so d short equals to d, then it takes a bit more to sample everything, but still it's like you have half of a second per each of Markov chains with 4 of them. So we can just plot what's going on, and we have very tight values for mean. We have relatively tight, small standard deviations of coefficients, as you can see here, and so our model is relatively confident about what it could learn from this data based on the structure that we have. We need to just evaluate how much sense it makes in the concept. Well, and it's not really bad. It's a simple model, but it gets most of as you can see, the data is relatively spread. There are some things that we just don't capture with this model, but for what it is, it's not that bad. We get our model gets us more or less good approximation of where we are on 90% of cases. If we look at our model's results, we see that alpha coefficient is very the mean is very tightly estimated, and as you can see, it's consistent with the histogram of actual measurements of people's height. So it captures a mean of that population very well, and beta is relatively small, located around 1, so it corrects our heights with respect to the difference from the centered values. And what we can use this model, we can, for example, consider what kind of prediction we could make for, let's say, a person of weighing 50 kilos. We could estimate from it how tall that person would be, and considering the mean of that coefficient of the mean, you can see it's very tightly spread between 158 and 160 centimeters. Of course, adding to that our standard deviation, which we have estimated here around 5, so we could always go 10 centimeters one way or another for 95%. So this is our mean, and this is what we could get from getting the adults. So we had a model. As you can see, changing the prior makes the relationships a bit better. The model is of course very simple, but we can still consider what kind of uncertainty we can expect. We can model that uncertainty for our entire dataset. However, we've created our model and tuned it and analyzed it for the adult population. How such model would work for the population including children? So let's consider all the data. So let's reload the dataset again, just to be on the safe side, and I want to add another concept that we'll be using generally in linear regression modeling, which is a standardization of variables. Standardization of variables is a method of changing the predictors and sometimes also the outcomes in a way that will remove units from the analysis and put all our data in the same scale. The idea is very simple. You just take your data, you center it, so you remove the mean from the population, and subtract the mean from all the elements of the population, and then you divide the results by standard deviation. This is useful because then our variable, generally our variables will now be represented not by, for example, in case of kilograms, but how many standard deviations we are far away from the mean. So really, how much the population is spread consisting from zeta. For normally distributed data, such coefficients just from getting the mean and standard deviation would be okay. In case if we are relatively sure that our data is not normally distributed, then perhaps it would be a good idea to do some prefitting of certain distribution to that data, and then subtract the mean and the standard deviation of that distribution from the sample, because in that situation we'll have easier representation of our data with what we wanted to do. But for this case, simple standardization, as you can see, it's much easier to interpret what we are going here. So generally we can see how certain coefficient is, for the weight, is characteristic for the sample or not. So for example, here is someone who is almost one standard deviation away from the mean of the weight. And of course, using either standardized or the centered variables doesn't change our model. We'll just change the values of our predictor coefficients. So for our beta will have different value, generally proportional to standard deviation when we will do the same refitting. So how our model will work for this situation, for the entire dataset, including children? Well, this model, generally nothing changes from our point of view, because we do the standardization, we can do the data fitting. So we just provide it with standard weight instead of centered weight, but does not change anything. It just changes the values of beta, because remember we had beta on the level of 1, now we have on level of 25, because our predictor now changes. Generally, if it's normally distributed, it should change from -2 to 2. So this will be the spread of this value, and maybe from -3 to 3 in more, if you want more extreme cases. And in this case, then the coefficient for beta has to be larger. So the numerical value of coefficients changes. And well, how our model will look like for this? Well, there we have some problems, because as you can see, the model for including the children is much more, it changes much more how it behaves. First of all, the standard deviation, the mean of the entire population is a bit skewed to smaller numbers. That's one thing. But the other thing is that this model is evidently nonlinear. This relationship between weight and height when considering entire population is not linear. There is much more complicated relationship. But this does not stop us from using linear regression, because, as we've discussed before, linear regression is linear with respect to parameters. With predictors, we can use any kind of functions of predictors. For example, we can add higher orders of predictors. For example, square second power of the weight. So our mean would be the combination of intercept, b1 times weight, and beta 2 times weight squared. And here, why standardization is useful, because if our variables wouldn't be standardized, then values away from the values can get extremely high quickly by squaring. But for standardized variables, the variables close to the mean, one standard deviation away, are being shrinked by squaring. So only the higher values will be influencing that much, and because of that, those coefficients will be on the same level, which will be useful because of numerical computation. because it doesn't change much on the level of model creation if there would be coefficients standardized or not. But standardization gives us a bit more interpretability, and moreover it puts everything on the relatively same scale, especially with powers can be very important. So let's do some prior predictive checks. We have our model. As you can see, this model is slightly modified by adding the second power of weight and beta 2. So we compile this model and do some fitting. This fitting is of course relatively fast because it's only one chain, and it took us, well, much less than 1 second. We only needed 1000 samples, and as we can see on this figure, the generally starting from samples, this mean of our initial distribution gives us away from the samples, because certainly there's a lot of population that was added that is smaller and lighter than those in the middle that was previously well represented. So maybe our prior of 178 is not that good, but on the other hand, it doesn't make much problems. It's still relatively wide, and it does not really influence anything because we can move from it away, but because we have enough data. So what our summaries look like, we get the at least for the simulation, we get again large spreads of everything, but we don't care too much. Our model is, well, it's not perfect, but this distance from sample value is not that much of a problem, so that we should care about it. We could change the mean of the prior for me, but from alpha, but it's not that really significant change that would change anything about our posterior. So having a model that does not generate obvious rubbish, we can now start to do some fitting. And again, here almost nothing changes. We just changed the definition of the second parameter. Here we've assigned the prior for beta 2, also here also, as normal. Why not log normal? Because here we don't have any justification of why this relationship should be negative. With the second power, we generally lose interpretability. With the first one, you can leave the positivity requirement, but for the second one, we don't really have any justification from that. So we just leave normal here, and we shouldn't care about it too much. And using this model, we can do some fitting, and so we can compile the model, and we can do some fitting. The data doesn't change. We've only added one more predictor, which is a function of the previous one, so the data is the same as previous. And here, this fitting took much more time because still under 1 second for each of chains, but it was visible that something was going here. And we got the information from the diagnostic from PyStan that we have too many parameters, and we have a lot of parameters because we have both parameters. We've computed both me and predicted heights, which are stored. We have over 500 samples, so we get a lot of parameters here. These means are not real parameters as here because they are functions of only those few parameters, but it will be useful for us to, and then no actual inference happens to those parameters, but still there are a lot of them, and we don't need to care about that. So getting those parameters, we can see how it looks like, and using our ribbon plot, we can see that, well, this captures situation much better for the smaller variables, because the spread of predictions is relatively well-covering situation. But again, this way is a bit tedious of changes this model, because adding additional predictor requires from us more complication in model creation, and maybe it could be done a little bit more efficient. Let's just look on the summaries. Again, we can see that the coefficient for the second power is negative and relatively good confidence of where it goes. So generally, we've added additional computation to our model because we require for our model to compute the square of each of the samples, and of course we've added also that here we have a for loop, so this will be slower by default. So generally, this is not efficient, and adding more predictors requires changing the code, which will be even more irritating later. Because of that, we can do something else. And what we will be doing, we will be creating so-called design metrics. Because really, our problem of adding additional predictor is really equivalent to the problem of multiplying to of matrix vector representation of our model. Because really, it's not a difference for us. Are we adding the computation of beta times first power plus beta 2 times second power, or we just get a vector of betas and we multiply it from the from the left side by a matrix consisting of first column that will be values of predictors and their second powers. Or if we want more, we can add more predictors, for example, a third power. And what we are generally doing it here. So we take our original data frame for all the people. We now adding two columns, second and third power, but we are just again doing with standardized variables, so we won't have this issue. Then we just create our design matrix from the last three columns. It will be a NumPy array, and we'll give up on the prior predictive simulation because it doesn't add that much here, and I just wanted to show you how just how the fitting works in this case. And we should of course do it again, but it generally wouldn't change much. For simplicity, I've gave up on assigning the log normal prior for the first beta coefficient because it will be easier for us to sample this situation. Here we have a model that allows us to submit any kind of design matrix for our model. And again, we have provided a number of measurements, but we now provide a new parameter, number of predictors. And with that, a matrix that has n rows and k columns. And this matrix will be our design matrix for our model. It's useful because we can pre-compute the values of, for example, squares and thirds powers before, so they won't be computed within every iteration of our model. Then of course we have parameters, but in case of beta parameter, we change this parameter to a vector. So now we will be sampling the k elements of beta vector, so which will be consistent for us to do this multiplication. Matrix X times beta. Here we are adding alpha, which is a number, but Stan allows us certain broadcasting capabilities. So alpha will be added to every element of this vector product, matrix vector product result. So, because beta is a vector, we can use vectorized notation, and we just can assign normal 0, 10 priors for all elements of beta. Alpha stays the same, sigma stays the same. We are now fitting this model consisting of linear combination of intercept, weight, squared weight, and cubed weight, and we are creating our model. So, with that we can do some fitting. The first compilation, then we provide the data. We are just adding the third power, so it's consistent with our design matrix that we had before, and we provide with the results. So we are doing the sampling. The sampling, because parameters are takes 1 second per each of iterations. Each of Markov chains, so we get certain results. And from that, we can get our parameters and we can see how it works. And generally, we can improve on our predictions even more. Our model captures even more wiggling of this situation. We've fitted a cubic model, which we can position us in the same way as committees related to US president who also used cubic models recently for predictions of COVID-19 pandemic but what we did here, what you should take from here. First of all, the regression problem is relatively simple to code here. We just used the design matrix and we got the results that we wanted by simple modifications of the model. So we just changing this matrix allows us efficient computation, and the model can capture this relationship. Of course, this is not the should be standard deviations. Sorry. This model is not a causal model. This is a predictive model. The predictive model of that allows us to predict height using the weight. We cannot infer about the heights by weight. Generally those two variables are correlated, and because of that we can get something. But as you can see, linear model does not limit you to linear plots. That's one thing, and allows you to adding more predictors. Generally, we won't be doing it now. You will be assigned a task for that. We haven't touched the other variables. We have both age and gender. Those variables certainly are influencing the heights of people, because there is certain gender modification changes of averages due to gender, and of course the age would be able to capture certain effects of that are present here for the children. So this will be ending of this video. Next time we will be doing more advanced creation of design matrix using splines for different model. However, there will be a task for you to use these techniques, but just add more predictors. So add the age and add the gender predictors and see how your model will look like, and you will be able to model relationships later. Thank you, and see you next.